Hello, I welcome you all. The problem reads, draw the shear and moment diagrams for the beam. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. Right, so to start with, we're going to draw the free body diagram. At the hinge A, we expect AY and AX like so. In the roller C, we expect CY. Right. So for this particular case, we have two spans that we are going to section, and the first span is from 0 to 2 meters, and then the second span is from 2 meters to 3 meters. Okay, so this will be my first section, but before we do the section, of course, and then this will be my second section. But before we do the section, let's find the support reactions. So we're going to apply the equations of equilibrium. We'll start with applying moments about A. So we have summation of moments about point A equal to 0 and clockwise being our reference. And for the distributed load from B to C, we are going to have an equivalent, and this is a rectangular distributed load. And this one is just the area under the loading, which is the height 1.5 kilonewtons per meter times the length of the load, which is 3 minus 2, it is a 1. Okay, so this distance here from there to there, this is the one we're calling 1. So this just gives us a 1.5 kilonewtons, and just acting at half the length of this loading, which is 0.5 meters. Right, so let's go ahead now and apply the equations of equilibrium. We're starting with applying the moment about point A. So we have minus 1.5. This is a negative moment, it's a clockwise one, so times 2.5 lever arm, and then we have plus cy times 3 equal to 0. Therefore, our cy is going to be equal to, let's grab our calculator, 1.5 by 2.5, then divided by 3. Okay, so cy gives us 1.25 kilonewtons, right? Yeah. So 1.5 by 2.5 divided by 3, 1.25. So found cy, let's find ay. So say summation of forces in the y direction equal to 0. Okay, what do we have? We have ay minus 1.5 and plus cy is equal to 0. So we have cy, which we just calculated, so we just replace it. So therefore our ay is just going to be equal to, let's find what ay is, minus 1.5 plus 1.25. Right, so our ay is a 0.25 kilonewtons. Right, and then we have summation of forces in the x direction, summation of forces in the x direction. Okay, so we have just ax equal to 0. So let's replace these values. We have 0 kilonewtons, we have ay, which is equal to 0.25 kilonewtons, and then we have Cy, which is equal to 1.25. Let me just get rid of this. 1.25. Cy is 1.25. Alright, so let's do our first section. If we did our first section here, okay, we're going to use the left hand side section. So we're going to have a beam, a section of a beam like so. Okay, a section of beam like so, with a loading at A here, support reaction of 0.25, okay, kilonewtons. Okay, and then we're going to have, so let's call this point as our section now, as section 1. So expect shear in this direction for our convention, okay, and then we expect also M1 there, right? And then if we are to apply the equations of equilibrium, let's take summation of moment about 0.1. Summation of moment about 0.1, we have 0.25. Of course, this dimension here is x, okay, so 0.25 times x. This one is a clockwise moment, which is negative, and then plus m1 equal to 0. Therefore, our m1 is just going to be equal to 0.25x. So this one we know is just a linear function with a positive gradient, right? And then let's take the summation of forces in the y direction like so. What do we have? We have 0.25 minus v1 equal to 0, and therefore our v1 is just going to be equal to 0.25. So this one is just a constant value, right? So we are done with the first section. So what we're going to do now is we do the second section. So we're going to section this there. Okay, so for this one I'm going to use the right hand side section. Okay, so let me draw right hand side to just be a piece like this. This point is C. I have a reaction there, which is a 1.25 cos kilonewton, and then I have some loading. Distributed loading, okay, and this loading is 1.5 kilonewton per meter, and I'm going to have my shear. This point, let me call it point 2. I have my shear going up like so, and my moment going in that direction. Then I'm going to have the equivalent force, this distance here. This one is x, okay, but going in this direction. Okay, we are going in that direction, right? We are moving from C going towards our point 2, and then this is going to be equal to 1.5 times x, which just becomes 1.5x, right? Okay, And then this distance for the loading, this one here, this one is just half of x, therefore it is just 0.5 0.5x, right? Okay, so I think we have all the information. This is a second interval. So let's take moments about 0.2. So say summation of moments about 0.2 equal to 0, and clockwise being our reference. What we have? We have minus 1.5x, okay, times the lever arm, which is 0.5x, okay, and then we have plus 1.5 plus 1.5 times x, and then minus m2 equal to 0. Therefore, our m2 is just going to be equal to, what do we have? This one becomes a minus 1.5 by 0.5. We have a 0.75 x squared plus 1.25x. Right. Is that what we have? So we have 0.75x plus 1.25x. Great. This is a polynomial of degree 2, right? So let's apply another equation, equilibrium equation, summation of forces in the y, like so. We have V2 minus 1.5x plus 1.25 is equal to 0. Therefore, our V2 is going to be equal to 1.5x minus 1.25. Alright, I think we are done with the equations. We have two sets of equations for the two intervals, right? From A to B, that's from 0 to 2 meters, which is here. Okay, and then from 2 to 3 meters, which is here, right? Great. So now let's draw the shear and force, shear force diagram and bending moment diagram. Right. So quickly, I think let's draw that. I'm going to draw 3 lines here. I want to start with the loading. I want to show the loading there. It will be much easier to relate. There we go. Let me just move this a little bit down since I still have some space. Alright, something like that. So we have here 1.25 kilonewtons, and then we have a distributed load there of 1.5 kilonewton per meter. Okay. Right, and the dimensions for this is as follows. This is 2 meters and this is 1 meter. Okay, this point is A, this point is B, this point is C. Okay. Okay, let me just draw these lines like so. These lines like so. And then the other line also like so. Alright. So we have positive up like so, negative. Say positive up there and negative. Okay. So there we go. This is the shear force diagram and this is the bending moment diagram. Okay, let's now do, plot the shear force diagram as well as the moment, the bending moment diagram. Okay, let me just move this a little bit down. Okay, something like so. So we have two equations for a shear. We have V1, and this V1 governs the interval AB. This is V1 here. And then we have V2, which governs the interval BC. You need to take note that V1, okay, was determined for the interval AB moving from A to B. And V2, okay, which is the function that governs the interval BC, but we are moving from C to B. That is very, very important. Okay, for this is how we did our calculations, and this is not the only way, it's just one of the ways. All right, there are a lot of different ways, okay, of taking intervals and so on, moving from which direction to which direction. This is one of the ways. Okay, so this is not the only way, there are a lot of several ways, okay, of arriving at the same solution. So now let's write down this result. So we have V1. When x is equal to 0, okay, V1 still remains just a constant value, which is just 0.25. And then when x is equal to 2, since the interval AB is 2 meters from A moving to B, just to the left of B, so V1 of 2, okay, is going to be equal to, again, 0.25. This is a constant value. All right. And then let's check our V2. V2, we said, is a linear function 1.5x minus 1.25. So here we are moving from C to B, all right? From C to B, but considering the interval BC or CB, doesn't matter. And this interval has the length 1 meter. So at C, when x is equal to 0, V2 is equal to minus 1.25, okay, at C when x is equal to 0, all right, because we are moving from C going to B, okay. And then V2 of 1, that is from C to B, the maximum interval is 1, so V2 of 1, okay, gives us the value 1.5 times 1 is just 1.5, so 1.5 minus 1.25, it gives us a 0.25. Okay, so this information is vital, so I'll write this in advance here. Okay, and then I'll do the plotting, then I'll come down here for the moment. Okay, so let me move this again a little bit down. Maybe I move this a little bit down again. All right, something like that. So let's start doing the plotting. So at A, we expect a constant uh, we have a constant shear, okay, of value 0.25 up to the left, just at the left of B. Okay. Immediately we go to the right of B. Okay, but we are starting from C. Okay, because that is how we are doing the sectioning. We start from C for the other interval. So for this one, V1 of 0, it is 0.25. V1 of 2 is 0.25, is constant up to the left of B. Then we go to C. C, V2 of 0, that is at C, when x is equal to 0, we have a value of 0.1, we have minus 1.25. Okay, and then V2 of 1, when x is equal to 1 from C to B, then we are going to have a value of 0.25, which meets this particular point here. Okay, that point there. Okay, there we go. So we have this point is 0.25 kilonewtons. We have this point here, 0.25 kilonewtons. And then with this one is a minus. So this is a minus, plus shear. Okay, there we go. And this one is minus, there we go. Right, so we've drawn this one and it's okay. So let's now draw the bending moment diagram. Again, we have two equations for interval AB and interval BC, just like we had two equations for shear. So we have for M1, which is this one here, it is a linear function, okay, 0.25x. So we'll write the similar information like we did in the other case. So M1, when x is equal to 0, it gives us moment equal to 0. And then M1, we are in the interval AB, when x is equal to 2, okay, 0.25 times 2, what does it give us? 0.25 times 2, it gives us 0.5. So our moment will be 0.5, all right, kilonewtons meter. Let's go to a second equation. Here we are starting from C, going towards B, because that's how we did our sectioning, and for this, that is how we worked on this particular method. So M2, when x is equal to 0 at C, what do we have? We have M2 equal to, here is M2 here, okay, M2 is a polynomial of degree 2, which is a quadratic. So we have minus 0.75x squared plus 1.25x. And when you look at this particular polynomial, it is of this nature, something like this. It opens upwards like this. Remember the negative, right? If it was positive, this one with the maximum power, if it was positive, it was going to be opening up like this. Okay, but it's not opening like this. It is opening down like so. Okay, it opens like this. All right. So there we go. So we are saying M2, when x is equal to 0 at C, moment at C is going to be 0, and it makes sense because we have a roller there. A roller, a hinge, you don't normally have a moment to support unless there's an applied moment, external applied moment. We don't have anything there. All right. And then we have M2, when x is equal to maximum of BC is 1. All right, so let's plug in 1 in there. We see what we have. So we have minus 0.75 times 1 squared plus 1.25. So this gives us a positive moment of 0.5 kilonewton meter. So let's start doing the plotting. So from A to B is 0.25x. So this is just going to be equal to a linear Okay, a linear curve. Okay, all right, something like that. Okay, and then from C to B, this is a polynomial with, of degree 2. This is quadratic, so expect it to open like that, like I had shown initially. We expect something like this. All right. So let's start from C, something like that, like this. Okay. Okay. I may not have drawn it properly. All right. All right. Mind you, there is this point here, which we found. This point here we said is 0.5 kilonewton meter. And then we have this point where shear, this point here, look at this point, where shear is equal to 0, this point here. This point here. This is going to be our maximum point for the moment. But we need to find this. For us to find this, we need to find the length from C to the point where shear, we need to find this length here. Okay. All right. And we can either use similarities of triangles, or we can use the same equation in the interval BC, which is this one, V2 equal to 1.5x minus 1.25. So at this point where shear curve cuts through the x-axis, we expect shear to be equal to 0. So shear at this point to be equal to 0. So if that is the case, therefore, the value of x will be equal to 1.25 divided by 1.5, which is equal to 1.25 divided by 1.5. So this gives us a 0.833. Okay, meters. And again, we are supposed to measure from where? From C towards B. So we are moving from C. So this one is 0.8333 meters. Okay, or just leave it as 8.33 meters, like so. So knowing that length, we know that the area under the shear diagram gives us the moment. All right, so this portion can give us the maximum, or this portion will give us the same value of maximum if we calculated the areas. So we can use whichever portion, either on the left or on the right. I'm going to use this one on the right. So my moment at max moment will be equal to half, this is triangular, times 1.25 times 0.83. So maximum moment therefore gives me, what do I have? I have half, which is just 0.5 times 1.25 times 0.83. So this gives me a 0.52 kilonewton meters. So let me indicate it. So this value here is 0.52 kilonewton meters. Right. So this moment here is positive. There we go. Something like this. All right. I guess we are done. In some books, you find that instead of showing the moment like this on top, they will show it at the bottom, which is also correct. All right. They'll just flip it and mirror it. They'll find it like this and just mirror it on the other side. Okay. Which is also just following the way the beam bends. Okay. When the beam is bending like so, you want to take the bottom fiber here okay, which is in tension, and the top 5 which is in compression. So we want to just have the conversion that follows the way the beam bends, right? So whichever method you want to follow, it is still correct. It doesn't really matter as long as you know what you're doing. All right. I guess we are done, and I hope the video was helpful. And if it was, give me a thumbs up, like my video, and continue subscribing to my channel. Bye bye, and see you in my next screencast.